Welcome to this physical review journal club of this month. My name is Ehud Yariv. I'm going to be the moderator. The talk is based upon an invited paper that was published in Pure Fluids in October this year. The paper is by Blaise Delmotte, who is going to present the talk. He's from École Polytechnique, and by Florencio Balboa from the Basque Center for Applied Mathematics in Spain. And the title is Modeling Complex Particle Suspensions, Perspectives on the Rigid Multiblob Method. The talk is going to be for 15 minutes. We will not take any questions during the talk. If you have any questions, please post them on the chat during the talk, or alternatively, once the talk is over, we're going to have 15 minutes for a discussion where you can raise your electronic hands. So Blaise, please.
Thank you very much, Ehud. So yes, this talk is about the modeling of complex particle suspensions. And first, I want to define what is a complex particle suspension. So basically, a suspension is a collection of particles that are immersed in a fluid. Okay, and here we will assume that these particles are small enough, and their velocity is also small enough such that the Reynolds number in the flow is very small, which means that they're going to live at low Reynolds numbers. And in this regime, their hydrodynamic interactions are long-ranged. And in addition to these hydrodynamic interactions, the particles can be of different types. That's why I call that complex suspensions, okay? And here I just give you some examples. This is not an exhaustive list, but for instance, these particles can be driven by external fields driving their motion. They can be linked together by kinematic constraints, like colloidal molecules, you can see here. They can be also sensitive to thermal fluctuations and diffuse in a complex way due to their complex shape. They can also catalyze chemical reactions on their surface, which can lead to spontaneous motion and symmetry breaking. And they can also use internal activity to deform and move in the fluid. Okay. So this is basically examples with a single particle, but of course, when you put many of them together, strange and fun things can happen. For instance, if you put many torque-driven particles together in a fluid above a wall, they can exhibit instabilities and collective motion, as you can see in this experimental movie. Another example is if you put many particles like proteins in the cytoplasm, their diffusion can be hindered because of a crowding effect due to the fact that there are numerous particles in a small space. Another example is the self-assembly of reactive particles that generate flows, and these particles, if they were isolated, would not move at all. It's because they see each other hydrodynamically and chemically that they can self-assemble and generate clustering and spontaneous motion like rotation or translation. So what we can see from these very few examples is that basically the interactions at small scales, okay, can really affect the collective and macroscopic behavior at the level of the suspension, okay, in terms of stability, rheology, diffusion, flow generation, collective motion, etc. And so if you want to understand this macroscopic behavior in terms of modeling, you're going to have to face some modeling challenges here. So of course, for the hydrodynamic interactions, you're going to have to solve the n-body problem, where n can be large, n being the number of particles. Because the particles, the hydrodynamic interactions are long range, this is a very highly coupled problem. In addition to that, the particles can have arbitrary shapes and non-trivial boundary conditions on their surface. And you keep adding challenges, of course, because they can have kinematic constraints linking them together. They can be subject to multiplicative noise if you have thermal fluctuations. You can have also surface reactions and flows, active deformations. These are also, again, just examples. So all of these challenges, of course, will lead to limitations because you cannot deal with large suspensions with analytical approaches. And usually the computational cost is pretty high for these kind of problems. That's why traditional methods are limited to spherical particles or few complex particles. So one of the methodological objective of a group of collaborators is to develop a unified framework to solve these fluid-solid interactions between many complex particles. And so this framework is based on a method that is called the rigid multiblob method. The idea is very simple. And actually, it's it dates back to the late 70s, where the idea is just to discretize the surface of the particle with spherical markers that we call blobs that have a finite radius and that are constrained to move rigidly together with the particles. Okay, and it was used 50 years ago to look at the aerodynamic coefficients of non-spherical particles. And since then, it has been applied for a wide range of particles. And here I'm just showing you examples of different ways of discretizing particles with complex shapes, from proteins to bacteria, to branch particles, to Möbius strips, etc. Okay. So beyond the idea, now I want to introduce just a bit of math, not so much. So let's consider that we have n particles immersed in a viscous fluid, okay, and we're going to call y their position and theta their orientation, okay. We're going to assume that we know the external forces and torques applied on them, and what we want to find is the resulting linear and angular velocities of the particles. That's what we call a mobility problem. So these particles are discretized with blobs on their surface, and basically what you want is that these blobs move rigidly, okay, with the particle, and for that you're going to introduce Lagrange multipliers that are forces, these lambdas, okay? And these lambdas are here to enforce the rigid body motion. So the blob velocity should move rigidly with up and omega p, the particle motion, okay, velocities and rotation. And what you see also in this relation here is what we call the mobility matrix. The mobility matrix gives you basically the hydrodynamic interaction between all the blobs of all the particles, okay, in Stokes flows. In addition to rigid body motion, you can also have surface velocities. That's a new addition from our work, where the surface velocity can have different natures. It can be due to ambient flows evaluated at the blob position, okay? It can also be due to the fact that you can have phoretic flows. For instance, in the case of phoretic particles, you can generate a slip velocity that's going to be proportional to the tangential gradients of concentrations or electric potential, if you look at electrophoresis. Then it can also correspond to active flows, such as the case of active particles. Here you see a particle with cilia, and you can model that as an active surface flow. And also, it can be due to thermal fluctuations in the fluid. That's something that was actually recently developed, as you can see from the papers, where basically here the blob velocity has to be proportional to kBt, the thermal energy, right? And times the square root of the mobility matrix between blobs due to the fluctuation dissipation theorem. I won't go further into details, but just to tell you that you can incorporate the effect of the thermal fluctuations at this level. So, okay, this is the boundary condition that the blobs have to satisfy, okay? Rigid body motion plus surface velocity. Here we have three unknowns. We have the Lagrange multipliers, the forces on the blobs, and the particle velocities and rotation. So to close the problem, of course, you're going to add the force and torque balance at low Reynolds number. The sum of forces must be equal to 0, which means that the forces due to Lagrange multipliers that are hydrodynamic in essence must compensate for other forces. So this actually can be written as a big linear system in matrix form, where you're going to have m lambda minus ku equal us, where k here is the Jacobian of this rigid body motion constraint, and kt times lambda equal minus f is the force and torque balance. Okay, so this is the system you want to solve, and here you can see that us can contain a lot of ingredients. Okay, already. You can solve that by elimination. Okay, and basically, what you're going to have is that the particle velocities are going to be proportional to the external forces through n. And n is what we call the particle mobility matrix. So this is the mobility matrix due to the hydrodynamic interactions between our complex particles. Okay, and here you also see the response of these particles due to these surface flows. Okay, so that's for the math. I'm done with the math now. So now let's say we want to simulate large suspensions of complex particles, and we want to do that accurately. So for that, to be efficient, of course, you need to solve this big linear system efficiently. Okay, and usually we use iterative methods. So we compute several products of this big matrix times this vector. Okay, and to be very efficient, we use block diagonal preconditioner. I won't go into the technical details, but basically we can solve this problem in a fixed number of iterations that does not depend on the number of particles in the system. Then you need to evaluate very efficiently the hydrodynamic interaction between the blobs, basically, which is this product n times lambda. Okay, you can do that either using analytical expressions, okay, because in Stokes flow we know the Green's function, okay, so we are able to have analytical expressions of the hydrodynamic interactions between spheres of radius a, okay, and we have that for a range of geometries. Or you can do that by solving the Stokes equation on the grid. And to couple the blobs to the fluid, what we're going to use are kernels, immersed boundary kernels, so are basically Gaussian functions, okay, that allow you to couple these blobs to the fluid grid. Okay, so you can use both approaches. Okay, you can use that as a black box. And what is nice is that nowadays we have fast methods to compute these analytical expressions. Okay. Direct parallelization on GPUs, fast multiple methods, Ewald methods, and also we have very fast solvers for the Stokes problem using immersed boundary methods that work for any kind of geometry. So if you don't have the Green's function for a geometry, you can use a Stokes, solve Stokes on the grid for the geometry. And then, of course, you want to do that accurately. So it means that you need to control the error that you make. So the bad news about the rigid multi-blob method is that the error converges quite slowly with the number of blobs, like the inverse of the square root. So basically, you need to go to use many blobs if you want to significantly decrease the error. The good news is that the prefactor in front of this error is already quite small. So basically, if you use a reasonable resolution, so tens of blobs on the particle surface, the error is about 0.1 to 1% at a distance, interparticle distance of a tenth of a blob radius. Okay, so it's not as accurate as boundary integral methods that are usually spectrally accurate to machine precision, etc. But here you get a decent error even in the near field that allows you to run large simulations. Then you can further improve the method by optimizing the grid. What I mean is that you can optimize the size of the blobs and their position relative to the particle surface to match the exact mobility coefficients of the particles. And in addition to that, has been done in some papers, you can also use pairwise corrections of near-field interactions, like you can do in Stokesian dynamics with lubrication. So now we have all the ingredients we need to simulate large suspensions of complex particles. And now I'm going to show you a few examples where it has been done in the literature. So first, I'm going to deal with colloidal suspensions. And one big interest, recent interest, is the effect of shape on the rheology of colloidal suspensions. There is a very nice paper, recent paper, where they show basically that where particles have a fractal shape or branch shape, you can have a quite interesting rheology, and you can have shear thickening that is very strong. So with colleagues, we try to simulate this system, and there is a more recent work by Florencio where he modeled basically branch particles with small hooks. Here you can see the hook shape, and what he showed is that the effective viscosity of this suspension with tens of thousands of particles can be very high for quite low volume fraction, you can see. And that's because the hook shape basically entangle together, okay? And due to thermal fluctuation, you can disentangle, of course. But what you can see is that by tuning the particle shape, basically you can tune the effective viscosity of your suspension. There are some colleagues from MIT who looked at the gelation of patchy spheres. So basically, if the adhesive properties of your gel particles are heterogeneous, then you can have different gel-like properties, and it also leads to different type of percolation. And also, the rigid multi-blob method is still used to look at the diffusion of molecules, for instance, at the individual level, but also the collective diffusion of complex particles, as shown here with boomerang-like particles. Then the rigid multi-blob method is also used to look at microorganisms. currently with one of my PhD students. We are looking at the swimming motion of diatom chains, a species that is called Basilaria paxillifera. We are using basically kinematic constraints basically to reproduce this motion, and we are doing experiments at the same time to understand how it locomotes basically. Florencio and his collaborators have looked at the motion of bacteria. It has been shown that bacteria have a flagella, and the flagella can be wrapped around the bacterium. And so Florencio and his colleagues have looked at the swimming efficiency of bacteria with a wrapped flagellum. And of course, you can do more than one bacterium, and that's something we showed with Florencio. Thanks to the scalability of the methods, we can do hundreds of bacteria interacting collectively above here, for instance, a no-slip boundary, where you see aggregation and complex motion. And here you have everything, aerodynamic interactions, swimming due to the flagella and steric forces between particles. The regime Multiblob method has also been used, to look at ciliated microorganisms. In this paper from colleague from Imperial College, they model a big sphere with the regime Multiblob method and cilia also with spheres, and they show that you have coordinated motion due to hydrodynamics. And I'm also currently working with colleagues in Hong Kong to look at ciliated propulsion using force distributions on the particle surface. The method is also used to look at active colloids, so reactive colloids, such as phoretic rods. It has been shown in previous literature that reactive rods can move against the flow. That's what we call rheotaxis when they are close to a boundary. And Florencio and other collaborators have shown that this is actually possible with great success by comparison with experiments. And the numerics are the hollow symbols here. And this was done thanks to the coupling of the rigid Multiblob method with thermal fluctuations and slip flow on the particle surface. They have also looked at the interactions of these particles with obstacles, and it has been shown, for instance, that they can circle obstacles for very long times. And more recently, we have looked briefly at their collective motion and show that reactive particles can form dynamic clusters that evolve due to thermal fluctuations and form also spinning gears. The method is also used in collaboration with experimentalists at Northwestern to look at the motion of microrollers. These are torque-driven particles above no-slip boundaries, like the ones I've shown at the very beginning. And what you see here are top views of these torque-driven particles that move toward the cylinder. And because of thermal fluctuation, they get trapped by the cylinder. And this is hydrodynamic trapping that is enabled by thermal fluctuation, which means that in the absence of Brownian motion here, you wouldn't see this long residence time of the microrollers. And we also played a bit with the method to look at phoretic stirrers, where basically in the literature, people have shown that if you have chemical reactions on the surface of anisotropic particle, this can trigger rotational motion, and this rotational motion can steer the surrounding fluid at low resonance number. And we have looked at large collection of these stirrers. And finally, I want to give a last example where we looked at the interaction between elastic objects and obstacles, fibers. That's work that has been done at LADIX with Camille Duprat, who does experiments, where you see a PhD student looked at the sedimentation of flexible fibers on obstacles, doing both experiments and simulation with a rigid Multiblob method, where the obstacles are discretized with blobs. And we were able to predict what happens in experiments where the fiber can glide along the obstacle or get trapped. And if the obstacle is non-spherical, we can have quite exotic trapping due to small friction at the obstacle surface. And then actually what we found, thanks to numerical simulation, is that if you put these fibers in a lattice of obstacles, then you can sort them by size or rigidity because of their interactions, hydrodynamic interactions with obstacles. And then more recently, and this is ongoing work, we have looked at very large suspension of fibers in porous media, in structural media, and look at how basically they distribute in space and their settling instability. So that was basically an overview of the rigid Multiblob method. What I want to tell you basically is that the rigid Multiblob framework is interesting because it allows you to interface with fast methods to compute hydrodynamic interactions between blobs. That allows you then to compute a large number of particles and obstacles. So really to model large suspensions with particles of arbitrary shapes. And as you've seen, you can handle multiple types of couplings simultaneously, reactive, suspensions, kinematic constraint, thermal fluctuations, all of this with a controllable accuracy. Most of the simulations you've seen, actually all the simulation, but two you've seen in these slides have been done with a code that is collaborative open source code, open to everyone. That is very simple to use. The idea is that it can be used by an undergrad student within a day. So basically quite simple to use. It's written in Python for the simple parts. The most technical parts can be written in other languages. And it has about 10 contributors and dozens of users. And here I want to pay a tribute to Alex Doneff from Courant, who passed away 2 years ago, but who was the real initiator of this initiative of this code. And now we are four basically main managers of the code. And of course, there are future directions to improve the method. As I told you, we are not very satisfied with the convergence of the method, so maybe we can find better ways, better quadratures to reduce this error. There are plenty of very nice ideas in the literature using fundamental solutions that could be translated into the method. And of course, the goal of this method, is to reach users, a lot of users from different physics and mechanics community, and that's what's happening right now. We have more and more colleagues that do experiments where the students are able to use the code on their own with just a bit of input from us. With that, I would like to thank you very much. There are much more technical details in the perspective paper. I want also to give you the links of the libraries where you have these very fast implementations of the blob-blob dynamic interactions that I talked about. And I want to acknowledge funding and thanks all the colleagues that contributed to this work. Thank you very much.
Thank you, Blaise. For some reason, I don't see any questions on the chat. I don't know if there is a technical error on my end. So what I propose is that if there are any questions, please just unmute yourself and start asking. Anyone? Okay, I'll start then. So you mentioned something that you called micro rollers, and you call them torque-driven. Can you please define what you mean by a torque-driven particle?
Yes, I will go to the first slide so that you can see better. Yep, this one. So these particles are basically rotated. So in the experiments, these are small particles, micron size particles, that have a small antiferromagnet in them. And what they do in experiments that has been done at NYU and now at Northwestern is that they use coils to induce a rotating, oscillating magnetic field. And basically, because the particles have a small magnet in them, they will follow this rotating magnetic field that will generate a magnetic torque on the particles. So basically, these particles rotate, above a floor due to this rotating magnetic field that rotates about an axis that goes here into the screen. And because of this rotation and the anisotropic drag due to the presence of the wall below, they will translate due to this rotation. So that's for two particles. And then we have done simulations and experiments with many particles. This is a top view where you see the particles from the top, and you see very interesting dynamics emerging from their hydrodynamic interactions.
Okay. I see there is a question by Pierre-Louis Martin. Maybe you want to ask the question?
Yes, thank you. Thank you, Blaise, for the talk. I was wondering on slide 24, you've shown multiple fibers. I was wondering how you handle collisions between the fibers.
So here we just put in this one, right? So here what we do is that we just put a pairwise repulsive potential between the blobs that discretize the fibers. So here the blobs are along the fiber center line. And basically just a pairwise repulsive potential that is short range. So really like we try to mimic a hard sphere potential, but of course we make it smoother because of the numerics.
Is this like a Lennard-Jones potential?
Yeah, here we use more purely repulsive potential, so like a Yukawa potential.
Okay, thank you.
There is another question by Yoshio Matsuki, who is asking whether the rock bacteria are real or only an artifact of the simulation. Can you answer that?
So can you just repeat the question?
Maybe I'll ask Yoshio Matsuki to ask you directly.
Yeah, actually, I saw your presentation, some simulation, the movie, and then there was something two. One is unwrapped, another is wrapped, and then wrapped microorganism, you said, and behaved a bit differently. So I was wondering if this is some real things or something artificial. That's my question.
I'm going to let Florencio, my co-author, answer that question because yes, I think it is real, but maybe Florent, you can answer that question better than me.
Yes, thank you, Blaise. Wrapped bacteria are completely real. They were discovered for the first time, I think, in 2017. There are several species that they have a single flagellum, and sometimes they swim with the flagellum extended away from the body. But when they are in very confined space, they tend to grab the flagellum around their own body. There is some group in Korea that they found this happens because there is some buckling instability in the hook that connect the flagellum to the body. And we found in a GFM paper last year that this configuration is more efficient to swim in very confined space. But the bacteria is real. It's really cool.
Thank you very much. The pipe, is this kind of the blood vessel?
So in the simulations, we use a circular pipe, and here we see a cut view to see the.
Right. Thank you very much. Thank you very much.
There is another question about the method itself, the numerical method. I'll just repeat it. This is by Sagnik Singha. Is the multiblob method able to resolve the characteristics of the flow itself? Or is it like the multipolar methods concerned only with the interparticle interactions?
Yeah, so yes, indeed. I think this depends on the way compute hydrodynamic interactions between the blobs. So indeed, in this formulation, right, you don't see the fluid velocity, right? You only see the particle velocities and the Lagrange multipliers on the blobs to enforce the rigid body motion condition, right? But you can have access to the fluid degrees of freedom if you solve the Stokes equations on the grid, right? If you want to compute the hydrodynamic interactions between the blobs by solving the Stokes equation on the grid using the immersed boundary method, then yes, you're going to have access to the pressure and fluid velocity field. If you use instead Green's functions, so mobility matrices with analytical expressions, then you don't have access to it. Okay, and then you need to compute the flow in a post-processing step, but you don't solve for the flow in the case you use analytical expressions.
What about the arbitrariness in choosing the blobs? You didn't. What is the effect on the numerical calculation, the accuracy?
Yeah, so that's something. Yeah, that's quite technical. So I didn't spend too much time on this. You're right. So basically, what we found. So what we try to do is to find the optimal ratio between the optimal spacing between the blobs and the optimal size. And one way to do that is to take the exact mobility coefficients. So you can use, I don't know, the best accurate method you can. And the mobility matrix is going to be a 6 by 6 matrix, right? And what you're going to do is that you're going to optimize the blob size and spacing to match this exact mobility coefficient. So that's basically an optimization problem that we solve to find the optimal blob radius and spacing. And then the way you place the blobs depends on the quadrature you want to use. But again, this is really secondary because the main error you make is, again, decrease like the inverse square root of the number of blobs. So basically, all you're going to change by optimizing the grid is the prefactor in front of this error. But what I was saying earlier is that even though we don't have a spectral convergence and we don't reach machine precision, we have, I would say, pragmatic, practical errors that are acceptable for large-scale simulations.
Any other questions? Maybe I'll ask another question on the numerics. So, what is the main who's the main competitor of this multi-blob method? Like, what was before, and can you say
Yep.
something about the comparison?
Yeah, so basically, so if you want to look at the interactions between small particles in Stokes flows of arbitrary shapes, you have what we call the regularized Stokes-Let method that uses Green's functions. But the problem with that method is that you cannot handle formal fluctuations. That's what here I show. Yep. So if you want to handle thermal fluctuations, you need the square root of this mobility matrix. So it means that this mobility matrix has to be a symmetric definite positive, and that's not the case for the regularized Stokes-Let method. So you cannot use the regularized Stokes-Let method for this kind of problems with thermal fluctuations. And also you have another method that is the boundary integral method, that is the most accurate one, but this one has a poor scaling in terms of number of particles. Usually when you look at dynamic simulation with the boundary integral method, you have at most 10 particles. So it really depends on the scale of the problem you want to look at. If you want to look at pairwise interactions or single particle, then yes, the boundary integral method may be better. But again, the boundary integral method does not handle thermal fluctuations in 3D. There is no available code for that or paper on that.
Okay. And this is going to be the last question because we are running out of time. So this is by Maria Kiel Jazewskawa. Can you please ask the question? Maria?
Blaise, I wonder if you compared results of your method with other approaches. Like, for example, there is an open source code that also uses Rotne-Prager-Yamakava for rigid particles, and there is a table of comparisons with different methods in this paper. This is by Żuk, Szymczak, and Cichocki. And also with some of the results for flexible fibers obtained by the hydromultiple, quite precise numerical programs that we are using.
Yeah, so yes, so if you look at, where do I have the reference? So if you look at in this paper from Florencio, I was also involved, and Alex Donef, so this paper, this is a long paper, 80 pages, where we do careful comparisons with hydromultiple, with other methods. And there you have a lot of extensive validations and comparison with other methods.
Okay, I think we are going to wrap it up. So thank you very much, Blaise. A great talk.
Thank you.
And have a fantastic rest of the day. Thank you.